Hi everyone. In this session I'll be looking at another special discrete random variable, which is the Poisson. So as usual, we'll start with the outcomes. First of all, know the definitions. Secondly, you must know the properties of a Poisson experiment. Then you must be able to solve problems using the Poisson tables. You must be able to calculate the parameters for a Poisson distribution. You must be able to solve word problems, and you must be able to use the Poisson to solve binomial problems by estimating the binomial problem using the Poisson. Now, consider an experiment where we are counting events, and the events that we are counting occur in a fixed time interval or a fixed area or a fixed volume. So in other words, if we consider a timeline and we have a fixed interval and we have another fixed interval of the same size, another one of the same size, then what we'll be doing is we'll be counting events inside of these fixed time intervals. Right, so that's what this is saying. Fixed time interval and fixed area, fixed volume. So fixed area might be squares or rectangles that we construct, and we'll be counting events inside of here. And then of course for volumes. Now, next, the time intervals or the areas or the volumes are non-overlapping. So from the image you just saw, I drew them next to each other. They are not overlapping. Then they are independent from each other. In other words, if you have one event happening in one time interval, it will not affect the occurrence of an event in another time interval. Now, if we let our random variable x be equal to the number of events in these intervals or areas or volumes, then we'll say that x is a Poisson random variable and it has a parameter lambda. Right, now this parameter lambda, we'll see in a moment what it means. So, if we have an experiment that satisfies these properties, and we let x be the number of events, then we can say x is Poisson. We'll denote it by using this notation where x tilde, or this little wavy sign, POI, which stands for Poisson, and then the parameter lambda. Now please remember that these parameters are always written in brackets next to the name of the distribution, just like for the binomial that you saw in another lesson where we had the parameters n and p, because these parameters determine how the distribution looks, right? How the PMF will look when we graph it. As these parameter values change, so the PMF will change as well. Right, now speaking of the PMF is given by this equation over here. So we have e to the negative lambda, lambda to the x over x factorial, and x represents the number of events. So we can have intervals or areas where nothing happens. So the minimum number of events we can have is 0, and the maximum will be infinitely many. Take note, x will be integers, okay, only whole numbers, because we are counting events. And of course, since we're counting, x can never be negative. Now lambda is the expected number of events per unit interval. Okay, it's the expected number of events or the average number of events per unit interval, and E is Euler's constant. So that's just a mathematical value that you'll find on your calculator, this one over here. Right, now let me just elaborate on lambda being the expected number of events per unit interval, exactly what that means. Again, consider our timeline, and we will have intervals that do not overlap, first of all. Secondly, they are the same size. Okay, so they don't overlap, they're the same size. And we have events occurring inside of them that are independent from each other. So we're counting events. Now for my example here, I have 1, 2, 3, 4 intervals. And in the first interval, I have 2 events occurring. The next one I have 3 events. The next one I have 2 events again, and the next one I have 2 events again. So these will be my events. So if I take 2 plus 3, that's 5, plus 2, that's 7, plus another 2, that's 9. Then the total events is 9. So the average per unit interval will be 9 divided by the number of intervals, which is 4. So this is going to be 9 divided by 4, so 4 goes into 9 2 times. We carry the 1, 4 goes into 10, 2 times as well. Then we carry a 2, 4 goes into 20, 5 times. So this will be my lambda, 2.25. Now please note, although we are counting events, the average of a distribution is not necessarily a possible value. Like in this case, the average is 2.25. We can't get 2.25 events. You can only get 2 or 3, but this is an average, so it is acceptable. Right, and then lastly, for the Poisson, a very nice result actually. The average is actually equal to the variance, and of course they'll both be equal to lambda. Okay, so very nice. Now before we get to an example, let's just see what the effect of the parameter lambda is on the distribution. Here I have 3 different Poisson distributions, PMFs, and each one has a different parameter lambda. Here lambda is equal to 3, here lambda is equal to 13, and here lambda is equal to 23. Above each bar, I've indicated the probabilities, just so that you can see that even though we can't see the bars, there's still probabilities over there. So let's start with the first one. For lambda equal to 3, we can see that the highest bars is situated around 3. So that means that the highest bar is at lambda equal to 3, where lambda, of course, is equal to the expected value, or the mean. For the next one, lambda equal to 13, we see that the highest bars again is by 13. So that means that the highest bar is around the expected value, in other words, the mean. If we look at the next one, for lambda equal to 23, then we see once again that the highest bars is around 23. So in other words, for the mean, E of x, we have the highest bars sitting around that value. Now, if we look at the shape of each one of these, where lambda is fairly small, equal to 3, this distribution is positively skewed because it has a long tail on the right-hand side. When lambda is slightly bigger, equal to 13, this distribution is still positively skewed, but it's not as bad as the first one because the tail on the left has become a bit longer. The tail on the the tail on the right has become a bit shorter. If we look at lambda equal to 23, which is now quite a bit bigger than the first one and the second, then we see that the left tail became even longer and the right tail became shorter. So this means that we have a distribution that's fairly symmetrical. So if we look at our conclusions, then we can say that for small lambda, the PMF is positively skewed. But as lambda increases, the PMF approaches symmetry, and it's symmetry about the mean. In other words, the mean will be in the middle, and the distribution will be tending towards symmetry around that value. Now let's have a look at an example. We are told that x is a Poisson random variable, and the average rate of events will be lambda equal to 5. So that means if we have a situation like in the previous slide where we have intervals or we have an area or volumes, then the average will be 5, and the way in which events happen in those intervals will follow a Poisson distribution. Now the question is, what is the probability of x equal to 2? Now graphically, this is how a Poisson PMF looks when lambda is equal to 5. Since lambda is equal to 5, okay, remember lambda is the average or the expected value. So since lambda is equal to 5, we expect most of the intervals to have 5 or close to 5 events inside of them. Okay, because 5 is the average. So that's where we expect most of the results to be. Okay, so if we count all the intervals, or rather if we observe all the intervals and we count the events that's in them, then most of the intervals will be close to 5. And we can see that over here. This is 5, which is the average, and we have the high bars situated around 5. Okay, high bars up to here, high bars up to there. So here they become a bit lower, there they become a bit lower. But the point is, the high bars are around 5, which is what we expected because the average is 5. Okay, so this means that there's a very high probability of getting an interval that has 5 or close to 5 events inside of it, and there's a very low probability, very low probabilities of getting intervals with events that are with a number of events that are far away from 5. You can see here, probability of getting 12 is very low. Okay, so this is graphically, but we won't always have a graph like this, so we need to use our PMF. Now we know that lambda is equal to 5, so we'll substitute 5 into our lambda, and this will give us e to the negative 5, 5 to the x factorial. We are interested in x equal to 2, probability of x equal to 2, so we'll substitute for 2 next. So this will give us 5 to the 2 factorial, and solving that we get 0.0842. In other words, there's an 8.42% chance that we will get 2 events in our interval if the average number of events per interval is 5. Okay, so graphically this is where it's going to be on our graph. And remember, the area is equal to the probability, and the height is also equal to the probability, because if we take the height and the width and we multiply it, it'll be the height times the width of 1 unit. So that will be the area, which is the same as the height then. Right, let's have a look at another one. In this case, we still have a Poisson where lambda is now equal to 3.5. Okay, so this means now that we expect the high bars to be around 3.5. Previous one, we expected the high bars to be around 5. Right, so let's see. If we substitute lambda in here, then we have e to the negative 3.5, 3.5 to the x, and graphically this is what we have. You can see here the highest bar is by 3. Okay, of course the highest bar can't be at 3.5 because we are counting events. Okay, so if your average is 3.5, it means that the highest bars will be around 3.5 if it can't be equal to 3.5. Right, and we are interested in probability of x equal to 2. So we'll substitute 2 again into our PMF, and we'll solve. So we see here that this probability is 0.1850, so there's an 18.5% chance of getting an interval where we have 2 events in the interval when the average is 3.5. Now you should recall from the previous one, the probability was 8%, approximately 8%. Now this one is 18.5. So why is this one a lot higher than the previous? Well, for the previous, we wanted the probability of x equal to 2 as well, but lambda was equal to 5. So we know that the high bars will be around 5, and the further away we move from the mean, see, the further away we move from the mean, the lower the bars become. So the further away we move from the mean, the lower the bars become. So that means the smaller the probability. So if lambda is 5 and we want x equal to 2, then we should expect a fairly low probability. But when lambda is 3.5 and we want x equal to 2, then we can expect a higher probability because x is very close to the average, which means we should have a really high bar for our PMF, which means a higher probability. Right, let's have a look at another example. Now in this case we have lambda equal to 15, but now we want the probability of x less than or equal to 10. So let's see. We'll substitute 15 into our PMF, right? So e to the negative 15 and 15 to the x. Graphically, this is how a Poisson PMF looks when lambda is equal to 15. Okay, so you can see that the high bars are situated around 15, which is that one over there. In this case, the average is a whole number, 15. So it means that we can actually get an interval that contains 15 events. So that's why you will have a bar sitting at 15. And you will see, of course, that 15 is the highest bar as well. Right, so we have the bars decreasing in size as we move away from 15, which is what we expect. Okay, the expected number of events per interval is 15. So if we're looking at, let's say, 28 events in an interval, well, then there will be a small chance of that happening. If we're looking at two events happening, it's also going to be very small. Now in this case, we're interested in x being less than or equal to 10. In other words, x being at most 10. So if x is at most 10, it means it can be less than or equal to 10 as well. So let's see. Because we're looking at less than or equal to, okay, less than or equal to, we're not working with a PMF now. We're working with a CDF because the CDF is cumulative. Okay, the CDF is cumulative, and that's what we want. We want the probability of x equal to 0 plus equal to 1 plus equal to 2 plus equal to 3 all the way up to x equal to 10. So graphically, we want all of these bars together. Okay, it is the CDF. Now, if we have to use our PMF calculation, which is this, it's going to be a very long calculation. Okay, each of these is equal to, we'll see each of these is equal to, so it means a PDF calculation for each, a PMF calculation for each one of these. But now instead of doing that, we can revert to our Poisson tables. Now for my example, I'm using a CDF table. We also get PMF tables, but my one is a CDF. So this is very similar to what we had for the binomial. So if we look at what is illustrated on the table, then we have these rows here, which contains different values for lambda, in other words, different averages. Now we saw from the previous examples that changing the average changes how the PMF looks, and that will of course change the probabilities. Right, because for this, our previous problems where we had lambda equal to 5, the probability of x equal to 2 was smaller than when lambda was equal to 3.5. Okay, so the same x but different lambda, it changes the probability. Right, so these rows are lambda values. Then in the first column we have our different x values, and then inside here we have the cumulative probabilities. Now this is just the first page of the table. There are many pages to this because we have many different lambda values. Right, now in our case, we're interested in lambda equal to 15. So this is the page where lambda is equal to 15. So if we zoom in a bit so that the numbers are a bit clearer, then we see there on the right hand side at the top, we have lambda equal to 15. Okay, lambda equal to 15. We're interested in x being less than or equal to 10. Okay, x less than or equal to 10. So we'll look for x equal to 10 over here. And then we'll check to see where the 10 row and the 15 column intersects, and that is at 0.118. So that means there is an 11.8% chance of getting an interval where the number of events will be less than or equal to 10, or in other words, at most 10. So in other words, we are considering all the intervals that contain either 0 or 1 or 2 or 3 all the way up to 10 number of events. Right, let's have a look at another example. It says here the average number of clients arriving per hour at a certain bank is 12. And then you're asked to calculate these four probabilities. Now let's have a look at this step by step. First of all, are we counting events? And the answer is yes. We are counting events because we're looking at the number of clients that arrive at a bank. Okay, so we are counting people. So we consider a person arriving as an event. So yes, we're counting events. Secondly, do the events occur in a fixed time interval? Yes, it does. We're looking at arrivals per hour. Now that means we are looking at hour intervals. Then next, are the intervals non-overlapping? Well, yes, it's stated here per hour. So that means, for example, we'll look at the number of people arriving from 8 to 9 o'clock, then from 9 to 10 o'clock, then from 10 to 11 o'clock, and so forth for the entire day. So the intervals are non-overlapping. And then another one, are the observations independent from each other? Well, I think it's safe to assume that they are. Okay? People arriving, one person's arrival will be independent of another person's arrival. So since we have all of these properties in our example, that means that we are looking at a Poisson distribution. So what we'll do is we'll let x be the number of events, okay, and that means then that x will be Poisson with parameter lambda. Now lambda is given to us. It says here that the average number of arrivals per hour, which is my interval, is 12. So if we add that information, then x will be the number of clients arriving, so that means x is Poisson with parameter 12, so it has this PMF over here. Now of course we can have time intervals where the minimum number of people is 0, and we could have intervals where there's a lot more than 12, but because the average is 12, okay, because lambda is equal to 12, we expect most of the time intervals to have the number of people around 12. Okay, so we expect a graph with high bars situated around 12 and lower bars as we move further away. Now let's have a look at solving this. First of all, probability of x equal to 4. Okay, so in other words, we're asking what is the probability of 4 people arriving in an hour? Now because it's equal to, we use the PMF, and that means we just take this equation, we substitute 12 and 4 into it, and we solve. And we see that the answer in this case is 0.0053, so that means there's a 0.53% chance of getting an interval where we have 4 people arriving. Now we expected a small probability because 4 is a lot less than 12, and we know that around 12 we have all the high bars, so in other words the high probabilities. So let's see, what is the probability of x being equal to 11? Well, again we have equal to, so that means PMF, so we simply substitute, and we see that the probability is 0.1144, so that means there's an 11.44% chance of 11 people arriving in a time interval. Okay, so we see that this is a lot higher than the 0.5% chance. Now next, we have a CDF problem, because this says what is the probability of the number of people being at most 11. Okay, remember, less than or equal to will be at most. So at most 11. So for a CDF, we have to go to our tables, because if we don't, it's going to be a very long calculation, because we'll need to add the PMF for 0, for 1, for 2, all the way up to 11. So we will look for the Poisson table, which has a row for lambda equal to 11. Sorry, for lambda equal to 12. I'm thinking of the x value now. Okay, so lambda equal to 12. So we identify that row. We have, or rather we identify that column. Then we have x less than or equal to 11. So we identify the row for x equal to 11. And then we check to see where the row and the column intersect, and that will give us a probability of 0.462. So that means there's a 46.2% chance of getting at most 11 people in an hour. Okay, so almost a 50% chance of getting at most 11 people in an hour. Now next, what is the probability of getting more than 11 people? Now personally, I don't like working with strictly greater than or less than for discrete random variables. I prefer to have an equal to. So this means greater than 11 will be greater than or equal to 12. Okay? Probability of getting 12 or more people, or at least 12 people entering the bank in an hour. Okay, so at least 12 people per hour. Now, this is a cumulative table. Okay, all the Poisson tables are cumulative. This is not cumulative. This is the opposite of cumulative. Okay, it's the complement of it. So in other words, I can take 1 minus the probability of x less than or equal to 11, and that will be the same as the probability of x greater than or equal to 12, using the complement rule. Right, now I've already calculated probability of x less than or equal to 11. It's the 0.462. So subtracting it, I get 0.538. That means there's a 53.8% chance of 12 or more people entering the bank in any given hour. Now the next section regarding the Poisson distribution is where we use the Poisson to estimate the binomial distribution. Now in statistics, before we can use any method, we always have to check the properties or the conditions that must be satisfied. So this is nothing different. X is binomial with parameters np, then it means that the expected value of x will just be n times p. This comes from the section on the binomial distribution. Now if n is very large and if p is very small, in other words, if we have a very big sample and the probability of a success is very small, then we can say that x is approximately Poisson distributed where lambda is equal to n times p, or rather lambda is approximately n times p. Remember, for a Poisson we need a parameter lambda. We know that lambda is nothing but the expected value. For a binomial we have two parameters, n and p, where n is the sample size or the number of trials and p is the probability of a success. We know that n times p is the expected value, so that means that when we have a large n and a small p, taking n times p, it will be approximately equal to lambda. Right, let's look at this example. An insurance company has 1 million clients. Each client has a 0.001% chance of dying of a certain disease in any given year. This disease is not contagious but genetic. For each client that dies of this disease, the company has to pay 100,000 Rand. First question, what is the probability of 2 clients dying in any given year? Second, what is the expected payout for any given year? So let's look at this step by step. First of all, each client has a 0.001% chance of dying. Now since it's each client that has the same probability, it means that we have a constant probability. And since we're interested in people dying, if you look at the question here, clients dying, expected payout, and the company will only pay if a person dies. So we'll consider dying as a success in this case, which is a very grim thought. But for our example, dying will be a success. So we look at the probability of dying and it stays constant. Now next we see that it says the disease is not contagious. So this means if the disease is not contagious, it means that it can't be transmitted from one person to another. So it means that people get this get this disease independently from each other because it's genetic. Okay, so it's independent from person to person. So if we say let x be the number of clients dying in any given year, then we can say that x is binomial with parameters 1 million and 0.00001. Now remember, binomial, we need two parameters, n and p, where n will be the number of trials, so in this case the number of people, and there it is, number of people. Probability of a success is 0.001%. We said that it stays the same for each person. This is percentage, so to change it to a probability we need to divide this by 100, so that's where the extra 2 zeros come from. And then lastly, it's not contagious, which means people get it independently from each other, so it's safe to assume that x is binomial. Now if we take n and p, then we see that n is very large, it's a million. P is really small, okay, 0.4 zeros and a 1. So it seems that we can use our Poisson approximation because this condition is satisfied. So if we take n times p, then we get 10. And what is n times p? N times p is nothing but the expected value, or in other words, the average. So that means that x will be Poisson with parameter 10. Right, so now we can answer the first question. What is the probability of 2 clients dying in any given year? Well, that means we need the probability of x equal to 2. Now we know that that will simply be e to the minus 10, 10 to the 2 over 2 factorial, using our Poisson PMF. Remember, Poisson PMF, we need to substitute lambda, so that's 10, and then we need to substitute our x value, and that's 2. I'm saying it is approximately because this is actually a binomial, but we're using the Poisson to estimate it. Right, so that all comes from the Poisson PMF. Now, an alternative way of doing this is to take the cumulative up to 2 and subtract the cumulative up to 1. So if we have the total probability up to 2 and we subtract the total probability up to 1, then we are only left with the probability of x equal to 2. So those two values will be 0.003 and 0.000. This comes from our Poisson table, which I'll leave for you as an exercise. You have the two demonstrations in the previous examples. Right, so we have 0.003, subtracting 0 leaves us with 0.003. And like I said, this comes from the Poisson table, so please go and have a look as practice. Right, then lastly, what is the expected payout for any given year? Now, to find the expected payout, we need to know how many people die, because we know how much is being paid for each person. So if we know how much is being paid for each person, and we can find the expected number of deaths, then we can just multiply the two, and we have the expected payout for the entire year. So the expected number of deaths is nothing but n times p. We've already calculated that. That is equal to 10. So the expected payout will simply be 10 times 100,000, which will be 1 million. Right, this brings us to the end of the Poisson.